Hello everyone. In this short video I want to talk about zero force members in a truss. So you know that if you do force analysis on truss members, which you can do either using the joint method or the section method, you can find that assuming that the members in the truss are two force members, you can find that some members are under tension, some members are under compression. But there might be some members that are not under any tension or compression. Basically, there is no load on them, so we call them zero force members. So the first thing is, how can we find them just by looking at the truss? And second, if they don't carry a load, why do we even have them in a truss? So first, let's talk about detecting them. Under what conditions we can expect to have zero force members? Scenario one is you have two members at a joint, just two members, and these members are not aligned, they are not along the same line, and either there is no load on that joint, or if there is, that load is collinear with one of the members. What does that mean? So look at this example here. If you look at this joint A, there are only two members, AB and AC, and there is no external force here. The external force is at point B. So if you do the joint method here, there is one force here and there is one force there, right? So this is F of AC and this is F of AB, and this angle is theta. So if you have the X and Y coordinates here, clearly, if you say sum of the forces along y equals 0, that is negative FAC times sine of theta is equal to 0. And since sine theta is not 0, that means FAC is 0. And then if you do sum Fx equals 0, that becomes negative FAB, and negative FAC cosine of theta equals 0. But FAC was already 0, so that means FAB is also 0. So if you only have two members at a joint that are not collinear, like these two, and there is no external force, that means both of these members are what? Zero force members. There will be no load on them. Yeah? Now, scenario 2 of this case 1 is there is a load at this joint A, but it aligns with one of these members. So let's say, for instance, here, you have this force F2. And now, if you draw again the free body diagram and add this F2, so all you would change is this F2 is added to the X equation, still in the Y equation. There is no force other than FAC, so this time FAC is going to be 0, but this FAB is going to be equal to F2. So now you only have one zero force member. Or if it was in this direction also, you can show that if it's in this direction instead, then this member is going to be 0, because you can write your equations in this direction instead of X and Y. You can rotate your X and Y, and so you can have this direction and this direction. And then any member, this direction. And then you can show that this one is 0, okay? So this is for what? This is the first scenario. Two non-collinear members at a single joint with no force or with the force aligned with one of the members. Scenario 2 is there are three members at the joint and no external load, and clearly you cannot have three members all on a line. So the member that is not aligned with the two others is going to be 0. Like if you look at this case, so at joint B, you have BA, BC, and BD, and since only BD is going to create a force in the Y direction, so that component has to be 0, which means the whole BD has to be 0. So in this case, this member BD is what? Zero force member. Okay? So now, before I move on to why we have these zero force members, let's look at a couple of examples that I found on some of the websites on Google. So we have these two examples here, and we want to see which members are zero force members. One thing important is, once you find the obvious zero force members, go ahead and remove them, okay, virtually, and then see if that leads to more zero force members. For instance, if you look at this one on the left, immediately you can focus on joint J, where it has two members not aligned, no external force. That automatically means that members HJ and IJ are zero force members, both of them. Okay, just like that. Then what? Then you can look at, for instance, joint B. And here you see there are three members, A, B, B, C, and B, E. And A, B, and B, C are aligned. There is no external force, so the left out member, B, C, that is not aligned has to be what? A zero force member, right? So you see, that's another one here. Then what? Is there anywhere else now that you can find zero force members? So before I do that, you need to determine the reactions of the supports here. In this case, A is a pivot, so A is going to have two reactions in general, a horizontal and a vertical. And there will be a horizontal because you have a horizontal external force here. And D is a roller, so it only is going to have a vertical force. So now if you look at joint D, there are two members at joint D, DI and DC, and there is this force, this reaction force, which is aligning with one of them, DI. So automatically here, DC has to be what? 0. So DC is also zero force member. Yeah? So now I got what? I got those four members to be zero force members. Now, before I move on to the rest of them, it's a good idea to redraw the truss with these four members removed, okay? So let's say you have this, okay? And as I said, any member that is a zero force member, go ahead and get rid of it. So you get this. And this one should also go. Yeah, so you have this. Okay, so we remove these four members, and this is the pivot, and this is the roller. And of course, these reactions and these external forces. Go ahead and draw them all. Now what? Is there anything else? Yes. Immediately you can look at joint H. Again, there is HG, right? And HI, which are aligned, and this HF, which is not aligned with these two, and there is no external force, so immediately you can say that HF is a zero force member. So that guy has to go as well. Is there anything else now? So I got that one off, okay? If you want, you can get rid of it. So let's say for a minute, we get rid of that one as well. Anything else remaining? You see, when that one goes, now you can see F. When that one is removed, now you can see F. And why could you see H? Because you got rid of HJ, sorry. So now, again, look at here, this FC and FI are aligned, FG is not aligned with them, and there is no external force. That means what? That means GF is also a zero force member. You see that? So we can get rid of that one as well. Here. Now this is the truss with members that are not going to be non-zero members. How can you tell? Because, well, let's see. Here at this joint, which is D, there is a force there and there is a member in front of it. They have to cancel each other. So this member DI has to be non-zero. Yes? Then here at this node, A, there is a horizontal and there is a vertical reaction. because there is a vertical reaction, this guy that is the only one that provides vertical reaction has to be non-zero. So this is clearly non-zero. Yes, for sure. What else? So you look at all different scenarios. Now, if you look at this joint E, if you look in this direction of EC, this two members, okay, or perpendicular, not EC, perpendicular to AG actually. So this direction is, because the way I drew it is kind of misleading, but if you look at in this perpendicular direction to AG, this force has a component, and this guy is the only one can have component, and they have to cancel each other. So that means this member EC has to be a non-zero force member. Otherwise, there will be no equilibrium. So this guy is definitely a non-zero force member. Okay, yeah? What else do we have here? Now here, these two reactions, if you call them AX and AY, the ratio between AY and AX is not necessarily the ratio of, or is equal to tangent of this angle, which means that the force AE cannot cancel both of those forces at the same time. So that means this member AB has to be non-zero to bring in the equilibrium. So AB can also be non-zero, and if that's the case, means BC has to be non-zero, so B is held at equilibrium. Okay? Yeah? And here, if AE is not zero and this EC is not zero, with this force P2, in the horizontal direction, because this member is determined directly based on P2, so the component of this member and that P2 along this direction of AC will not necessarily cancel each other, so EG has to be non-zero. And if it goes like that, when that is the case, then both of these have to be non-zero, that is non-zero, and you can show that the other members are also non-zero. So here we had what? We had, in general, if you just paid attention, 6 members that were zero force members. Now, if we look at this example here, again, you can see that G is a single joint with two members, no external force, so both FG and GL has to be zero force members for sure. Yep. Anything else that is similar? Yes. If you look at joint D, 3 members, 2 of them aligned, no external force. That means DJ has to be 0, just looking at it. And a similar scenario for B, BH has to be basically 0 force member. So these are obvious. Good. Now here, what we do is we get rid of these 4 that are obvious, and we draw what? We draw the rest of it. See what we can do. So here, and then here, right? And then here, here, and here. Okay, and I guess I need to trim this down a little bit. So this one probably as well. So let's go ahead and redraw everything. This guy is pivoted. This guy is a roller. And you have a member here. Correct. And that's it. And we put the external forces. So there is one here, there is one here, there is one here. Now in this case, there should be 2 vertical forces to cancel these guys, right? So what I will have is 1 force up here and 1 force up there. So some of those will give some of the forces in the y direction 0, as well as some of the moment about 1.0. Now, since there is no x force in this case, externally, there will be no x force for this pivot, okay? There will be no x force. You don't need any x force here. So these are the forces that we have at these pins. Now, is there anything else that you can see which will tell you there is a zero force member as well? And the answer is yes. If you look at this joint, there are two members and an external force that is aligning with one of the members. That means this guy here, which is your LK member, has to also be zero. Now, in the website that has published this picture, the only members that are considered are these four, while clearly LK is also a zero force member. Okay, and that one is not mentioned, so here I'm correcting for that. Okay, this picture is not from me or anybody, but clearly you see that member is what? That member has to be a, it doesn't, when I draw it like that, that doesn't mean the truss is like that, okay? Here you don't have a stability. But by removing them virtually, we are just looking for other zero force members. Okay, yeah? So it doesn't mean they don't physically exist. So here, this member is clearly non-zero, and that means at this joint, this guy has to be non-zero, and that means this one has to be non-zero. And then here, both of these are needed for equilibrium. Yes, and you can go forward and see the rest of it too. For instance, since this one is non-zero, that means these two are non-zero as well. Okay, they have to be. And now, if this force here does not cancel this reaction, which most probably doesn't, that means this guy has to be non-zero to bring the y equilibrium. And if that's the case, now if the x component of this member here is not the same as this one, then this guy has to be non-zero as well to bring in equilibrium. And you can move on like that as well. Right now that this one is non-zero, this guy has to be non-zero to bring in the y equilibrium. And again, if the x of this and x of that will not cancel, or the x of this is not canceling the x of those two, this guy has to be non-zero and can move on and so on. So here you see there are 5 non-zero members. Okay, now let's go about the final important million-dollar question. If these members are not really carrying any load, why do we use them, right? And the answer is they have two important tasks to do. One is they increase the stability and rigidity of the truss. For instance, one of the things they can do, which is the most important thing, is they prevent buckling of long, slender members under compressive loads. So if you look here, if I physically remove one of these force members, what's going to happen? Remember this one and this one were zero force members, right? If that's the case, what's going to happen? I just draw this portion of it. So you're going to have this. Since these two members are not needed, I won't need joint F. So CI is going to be this long member. Okay? But if I put this joint here and break it into two members, IF and FC, now I'm dealing with two shorter members compared to IC. And you know, in buckling, if you remember, the force of the buckling is proportional to what? 1 over L squared. Yes? So if I make the truss 2 times shorter, the buckling force I need for it is going to be 4 times bigger, and that means adding to the stability and rigidity of the object against buckling. Yes? The other one is, in case the loading conditions change, then you can have support. For instance, here, you say, well, this is the loading that I have, and based on that, I do a design of a truss. But what if at one of these joints also comes in some load is applied, like right at J? What if some load like this during working operations, working conditions, there is some external force F that is applied right here? If you don't have these two members, then that force is going to come right in the middle of member HI and it is going to bend it. Remember, in trusses, we want what? We want the forces to apply at the joints, not in the middle of the members, and it can bend the members, right? Yeah? Or, for instance, in this case, if there is at any point any load here applied at this F, at this point F, any force, then these two guys, one of them can carry it and basically not allowing for this point F to just sag downward. Or in this case here, right? If there is any load applied here, or some load applied there, or some load applied there, I have a member that I can use to cancel that force. So you see, it brings stability and it brings resistance to what? Unknown loading condition in the future. So that's why sometimes we add these members, because we predict some load might happen at some conditions, and we also want to shorten the slender members, make them more resistant to buckling. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.